Hello friends, myself Dr. Nandakumar Rao from College of Engineering Ambazogai is going to deal with numerical methods in mechanical engineering. This is our 14th lecture. In previous lecture, we have discussed complete pivoting, scaling and scaling with pivoting for the solution to the algebraic equations. Now today we are going to start the next unit where we are going to study numerical differentiation and integration. So here we will have the introduction about differentiation and what is integration in brief, then the applications of differentiation and integration, Newton-Cotes integration formula, then the trapezoidal rule. Now we will discuss what this differentiation means. So the differentiation means to make off by differences. Differentiation means to make off by differences. What is this means? Say for example, you are moving from one place to the another place, from place 1 to 2. So the total distance between 1 and 2, let it be y, and this distance which is covered by a person between place 1 to 2, which is y meters, is completed in t time, that is t seconds. So this distance is total distance is y meter and it is covered in t seconds. The rate at which this distance is covered, if you want to find out for very small time how much distance it covers, then we find out the velocity v is equal to y by t. So y by t, if we are going to take complete y by t, it gives per unit time. So instead of that, if we find that small change in distance y to the small change in time, so where time delta t tends to 0, that is very small time. So we want to find out the distance covered by a person for very small time, which is approximately equal to 0, not 0 but approximately equal to 0. This distance covered, which is delta y, and that delta y for time delta t is nothing but the differentiation. So that is nothing but differentiation means to make off the differences. So that is nothing but the rate of change of dependent variable with respect to independent variable. So which is dependent variable? So this y is dependent variable and t is independent variable. So now what we say here, the rate of change of dependent variable with respect to independent variable is a differentiation. Let's say xb, the independent variable, and f of x b, the function of x which is dependent. That is nothing but, say for example, f of x is function. It may be x square plus of 3x plus of 7. So this, the value of x, if we change, the value of f of x is also changing. That's why f of x is known as a dependent variable and x is independent. Independent variable. So now let us assume that very minor change in independent variable we consider delta x. If delta x be the change in independent variable, therefore if x is the change in, and delta x is the change in x, then the function changes to f of x plus delta x be the function at x plus delta x. If we are substituting this x as x plus delta x, then function value changes from f of x to f of x plus delta x. Now if we find out the change in the dependent variable, so change in dependent variable means, so f of x is the initial value of function and f of x plus delta x is the new value of function, where x changes from x to delta x, where x changes from x to x plus delta x. Very minor change happens, so x plus delta x is the new value of the independent variable. Therefore function which was f of x now changes to f of x plus delta x. Now let us see, so this change in this function, if we want to find out change in the function, is given by f of x, which has changed from f of x to f of x plus delta x. So f of x changes to f of x plus delta x, that is nothing but f of x plus delta x minus of f of x. So this is nothing but the change in the function, b the change in the dependent variable. Dependent variable changes from x to f of x to f of x plus delta x. So difference can be taken. So for example, initial value is 7, final value is 10. Then the difference of 7 and 10 is 10 minus 7. So that is change in the function value. This is for example. Okay. Now what we can find out, the rate of change of dependent function with respect to the independent function. So delta y by delta x we can write as, so change in the function is f of x plus delta x minus f of x, whereas change in the independent variable is delta x. So where this delta x is allowed, now if delta x is allowed to approach zero, the difference becomes derivative. Then the difference becomes derivative. That is nothing but Therefore dy by dx is equal to limit delta x tends to 0 means it is approximately equal to 0, which is equal to f of x plus delta x minus of f of x divided by delta x. So graphically, if we want to represent this, we'll have a graph. So on x-axis we take independent variable x. On y-axis we take dependent variable f of x on y-axis. Let us consider the value of independent variable as x, and the function value will be f of x. So this function value is f of x at the independent variable x. So now if we plot this function, it gives this graph like this, say. So if we find this graph like this, if we find out this function value for various values of x, then we get this path. So if we have n number of x values, if we substitute all values in this function f of x, then we get every new value of function f of x, and that we plot. Say for example, f of x, as already I told you, f of x may be any function. It is x square plus 3x plus of 7. So it may be any function. So when we change value of x, then function value of x changes, and if we plot these points on this graph, then we get a new path, and this graph or this curve, we call this as a function f of x. This represents function f of x. Let us consider first point where x is the independent variable and f of x is the dependent variable. So we get this value. So now when we change this x to x plus delta x, so if we change this x value from x to x plus delta x, then new value of independent variable is x plus delta x, and corresponding to this, if we plot a point here, so this is the point where f of x function value is going to be f of x plus delta x. So this is how it is represented. So now if we see here, this distance we call y-axis or delta y, that is change in the function, whereas this distance which we call as change in the independent variable, that is delta x. So this is delta x, this is delta y. Now what is this integration that we want to see? So now inverse process of differentiation in calculus is known as integration. Inverse means reverse. The inverse process process 2 differentiation in calculus is known as integration. Now what is this exact meaning of integration? It is nothing but adding together or uniting together. Integration means to bring together. Integration means to bring together or to add or to unite. That is nothing but integration I, which is equal to integration from a to b f of x dx, which you already have studied, stands for integral of function. This stands for the integral of the function f of x with respect to the independent variable x, evaluated between the limits of integration between the limits of integration that is x is equal to a to x is equal to b. The function f of x, which is here, this function f of x is known as the integrand. The function f of x is known as integrand. The meaning of integration is total value or summation of function f of x over a range x is equal to a to b. So the meaning of integration is total value or summation of f of x over a range x is equal to a to b. So now we will see here with the help of graph. Let us consider say this is on x-axis we take independent variable x, on y-axis we take f of x on y-axis, and we have one polynomial, say one polynomial which is the polynomial f of x plotted on graph. Now say we are interested to find out the area below this polynomial. If we want to find out area below this polynomial, how much is this area between 2 points, between point A and B. So our interest is to find out this area below this polynomial curve f of x. So this area we want to find out. In order to find out this area, we take help of integration. So integration is nothing but addition, or we divide this complete area into small areas and we add the small areas to find out total area below this curve. So this curve is nothing but function f of x. So this is what we say is, for function laying above x-axis, laying above x-axis, the integral expressed corresponds to the area under the curve f of x between x is equal to a to x is equal to b. So similarly, so this area can be obtained by this integration. So integral I is equal to integration a to b f of x dx gives us area below this curve or function. Now if function is f of t, so we take another example. If the function is f of t, it is function of t where time is independent variable and f of t is dependent variable, specifies the position of object as function of time. This f of t is function of time. The differentiation provides means to determine velocity. How we define velocity? Rate of change of position with respect to time is velocity, that is v of t. Velocity of the object is nothing but differentiation of function f of t with respect to time t dt. So conversely, opposite to it, if we want to find out function f of t, then if we integrate this velocity, integration from 0 to t, say for example, then vt dt gives us the function value f of t. So this is about the integration. So now we will see what are the applications of integration and differentiation. So first we see applications of differentiation. So now what we say, according to Newton's second law, change of position with respect to time is velocity. So this is a first application. So Newton's second law. According to this, we define velocity as velocity is defined as rate or change of position with respect to time. That is nothing but, say for example, here is the object at first location and it moves this distance and reaches second location. So this total distance we call as a s. So this is the distance s which is covered by this object in time t. Therefore, what we say, the velocity v is equal to ds by dt. So this is how we define velocity. This is first application. Then according to the Fourier's law of heat conduction, here we have a slab and here there is a source of heat. Here there is a source of heat or heater, say. This heater is dissipating heat and giving it to this object, and this heat starts to move or starts to pass through this material. So let us say this is the position 1 and this is position 2. Let the distance between these two is delta x. Delta x is the distance between first position and second position, whereas T1 be the temperature at first position, T2 be the temperature at second position. That is nothing but delta T be the temperature difference. So this amount of heat which is transferred from first position to the second position is directly proportional to the difference of temperature. So heat transferred or heat flux is directly proportional to the change in temperature, whereas this heat flux is inversely proportional to the distance. So heat flux is also inversely proportional to the distance between two positions or 2 points, that is delta x, 1 by delta x. So combining these two, what we can write is heat flux is directly proportional to delta T by delta Ex. So here this is written as heat flux is equal to K delta T divided by delta X. So if this X tends to delta X tends to 0, then this can be written as K dt by dx. So this is nothing but heat flux is obtained in this Fourier's law of heat conduction using the differentiation. So assuming that, so this change in the distance x is very small, so what will be change in the temperature for that small distance? So that is known as a heat flux. So heat flux can be obtained using differentiation. So these are the few applications of a differentiation. So this is how we are using differentiation to find out the various rates in our day-to-day applications. Now, what are the applications of integration? What are the applications of integration? Let us consider some field area. So this is the land situated, and here there is a drainage or what you say canal which is passing or river is passing through this or beside this area. Now we want to find out this total area. In order to find out total area, we split up this complete area. So it is difficult for us to find out this area of land. So that's why what we do, we divide this into small rectangles of unit area. So we draw horizontal lines here like this. Like this, and then we draw vertical areas like this. And here we count these small areas, that is rectangle 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31. So this is 31 units, are complete 31 units. So approximately this area is 31 to 32 units. So it may be 32 unit square area. So we have divided this complete area into small unit areas, and we have counted these small squares, and then we are going to say that it is approximately 32 units, square units. It is approximately 32 square units. So this is nothing but integration. What we are going to do, this complete area we are dividing into small rectangles. So here this small area is neglected, this small area is neglected. So whichever is larger, that is considered. And anyhow, we have measured 32 rectangles or 32 squares. Maybe some squares which are partially here. So adding these small squares, one more unit may be added, 32 to 33. So this is approximately equal to 33 square units. Area is up to 33 square units. Sometimes we want to find out this volume or area of a drainage or dam. So we want to find out this volume of water stored in this lake. So we know this profile of lake. Then at that time we find this distance, height at each point, and then we find out this area of cross section, and from this area of cross section we find out volume of water. So approximately it gives the water present in this dam. So this is how the integration helps us to find out the total volume of water in this reservoir or the area of land. So this is how the integration is used in day-to-day life. Now we'll move towards Newton-Cotes formula. Now we can see here. So what these Newton-Cotes formulas are. Newton-Cotes integration. So now say here integration I is equal to integration from a to b f of x dx, where f of x is the polynomial, where f of x is a polynomial of the form or this can be written as integration a to b fn of x dx. So this fn of x is a polynomial of form fn of x is equal to a naught plus of a1 x1 plus of a2 x, sorry, a1 x1, it is a1 x a2 x square plus of, and so on, plus an x to the power of n. So this is one polynomial. So now if we plot this polynomial on various graphs, say here, this is first polynomial, first graph, second graph, third graph we consider, and fourth graph. We'll have this polynomials. So this is polynomial of 10. Same polynomial f of fn of x. This is fn of x, fn of x, fn of x, fn of x. So f of x is represented on y-axis, x is represented on x-axis, f of x on y-axis, and x on x-axis. Now we want to find out area between 2 points A and B, say. So we consider 2 points between which we want to find out area from point A to B. For everywhere we want to find out this area, say area below this polynomial from A to B. So this is point A to B. Want to find out area from A to B. Now see here, we want to find out area where in first case see, in first case we take first order polynomial a straight line. So from this point to this point we assume that this is the curve. We want to find out area below this curve. Instead of that we consider only straight line between 2 points. This is the straight line which we call as a first order polynomial. First order polynomial is straight line, and we want to find out area below this straight line. And it is very simple for us to find out area below this straight line. So there will be error. So this area we are not going to consider, only the area below straight line. Actually we want to find out area below this polynomial, a red curve. But instead of that we are approximating this curve as a straight line by first order polynomial, and we are finding the area below this first order polynomial. Now in second case what we do, instead of assuming a straight line we assume a parabola here, and we are interested to find out area below this curve polynomial f of x red line, but instead of that we approximate this polynomial as a parabola and we find out area below this parabola. Actually we are interested to find out area below this red curve function f of x, but we are approximating this by straight line, sorry, a parabola, and this parabola, which is shown by a dotted line, and we are finding this area below this parabola. So this is in figure 1, figure 2. In figure 1 we are assuming this function by first order polynomial. In figure 2 we are assuming it as a parabola. In figure 3 we are going to consider various points on this polynomial, say 1, 2, 3, 4, 5, and then we join this first point with this second point, third point, fourth point, fifth point, and we divide this into strips like this. And this area below each strip, below this each straight line, we are going to find this area, then second area, then third area, fourth area, fifth area. So actually our aim is to find out area below this red curve, but instead of that we are finding area below these small segments, and these small segments are known as the small segments which we have approximated instead of curve are known as a series of polynomials. Instead of assuming a single polynomial, we are assuming first order polynomials, which are n number of polynomials. So this is one thing. Now second, one more method, that is figure, this is figure 3, say. In figure 4, what we do, we divide this into strips. So here we have taken strips like this. These lines are inclined lines, but here what we do, you see, so this is taken here, first strip, then this is taken approximately at the center, then second strip, then this is taken up to here, then third strip, then this is taken up to here, and approximately this at the center. So here this area is excluded, this extra area is included. So here this complete area below this straight line, so these horizontal straight lines are known as series of zero order polynomial, series of zero order polynomial, series of zero order polynomial. So this is known as a strip method. We call this as a strip method. In this strip method, say for example we want to find out this area, and what we do, instead of finding this area below this curve, what we are doing, so here we are taking two strips, and here exactly we are finding a straight line. So this area is excluded, this area is included. So this is subtracted, this is added. That means we are going to convert this complete into rectangle. So actually we want to find out this. So you can see here. So this area which is lost by us, and this area is extra area which is gained. So what we assume, that this area which is lost is equal to area gained. So this rectangle we are going to equate to the area below this curve. So this is nothing but in the strip method. So now there are two forms of Newton-Cotes formula, that is closed and open forms of Newton-Cotes formula. are available. Closed and open forms of Newton-Cotes formula are available. What are these closed form of those Newton-Cotes formula? So the closed form is we have two ends, that is lower end and upper end. So we know A and B. So the closed form are those closed form are those where data points at the beginning and end of limits of the limits of integration or no. Where the open forms of integration limits have extended beyond the range of data, that is called as extrapolation, interpolation and extrapolation. So the open forms have integration limits that extend beyond the range of data. What is this extrapolation and interpolation? Say for example, we have set of data, say we know x and y. For x is equal to 1, y is equal to 5, x is equal to 2, y is equal to 10, x is equal to 3, y is equal to 15, but we don't know what is value of y at x is equal to 4. So this is the data, actual data is this much, and but we are in need to know what will be the value of y when x is equal to 4, or if x is equal to 5, what will be the value of y. So what we say here, this may be 20 and this may be 25. At x is equal to 5, y is equal to 25, but this is not given in this table, so this data is not available in this table. Only table or data which we have is only this much. So even though based on this data we are going to say that at x is equal to 5, y is equal to 25, what we are going to do, we are going to find approximate value of y at x is equal to 5, which is not within this table, that is called as a extrapolation. So that is known as extrapolation. So for example, if we want to find out what is value of y at x is equal to 1.5, so at x is equal to 1.5, y value is not known. If we find out y value at x is equal to 1.5, that is known as interpolation. And if we find out something beyond this limit of data, that is called as a extrapolation. So today we stop here. Next class we will move with the trapezoidal rule for finding integral using a numerical integration method. So how to find out numerical integration, that is the trapezoidal rule, will be discussed in next lecture. Thank you.